So practice question from the textbook here. I'm just pulling these out of section 5.5. Number 3, balance reaction equation for sodium and chlorine gas to produce sodium chloride. We're given the limiting reagent here. 0.75 grams is to be completely reacted. That's another way of saying it will be the limiting reagent. Okay, completely reacted, so we can say that sodium is our LR, chlorine is our ER, excess reagent. So what is a reasonable mass of chlorine gas to use in the reaction? First thing we want to identify that this is a type A problem. We're not having to identify which reaction or reactant is limiting, we're told. So what is a reasonable mass? What's read into reasonable is, let's make sure we have minimum plus enough to make the reaction completely consume that 0.75 grams. So first thing we need to do here is calculate the number of moles of sodium. So we can take moles of sodium equals mass divided by molar mass, which is 0.75 grams. Molar mass of sodium is 22.99 grams per mole. So we can divide by 22.99 grams per mole. Okay, that will tell us how many molar units of the limiting reagent we have. That gives us 0.0326. I'm going to underline the second significant figure because that's as far as I can go with my significant digits. Now, according to this, we would need, and I can state this as a minimum amount of Cl2 is twice the number of moles of, or sorry, half the number of moles of sodium. Okay, so sodium is in a 2-to-1 ratio since moles of chlorine is half moles of sodium. Okay, so that means that we would need at least half of that amount. I would keep 0.75 divided by 22.99 on my calculator, and I would just take that and divide by 2. Okay, so that would be 0.0163. Okay, and that is approximately. And then I would just say that, well, we're going to try to find a mass, so we're going to need to convert back to mass before we apply the 10% excess, so we can apply it right now. Okay, I can say the excess amount would be 110% of this amount. Okay, which is, let's multiply that by 1.1, about 0.0179 moles. And then the last step would be calculating the mass of chlorine, which in this case is number of moles times molar mass. The molar mass of chlorine gas, Cl2, is 2 times 35.453, which is 70.906 grams per mole. So if I take that and I multiply by my 0.0179, I'm going to get finally my answer here. So 2 significant digits would be about 1.3 grams. Now I'm rounding to 2 significant digits because I'm done my calculation. Okay, so I notice I've added the 10% to the moles, not to the mass, and that's your choice. I've used a mole ratio in this step here, and I've done a couple calculations with mass to moles and moles to mass, so it looks a lot like a stoichiometry problem, and this is part of it. Okay, let's look at number 2. Number 2 is a type B problem. Here we're reacting 4.55 kilograms of sulfur dioxide and 2.88 kilograms of oxygen gas. Now they're just available. Okay, so this is a reaction that is involved in the formation of acid rain. Synthesis of sulfur trioxide from sulfur dioxide and oxygen gas. So sulfur dioxide is SO2. It's a gas. Oxygen is diatomic. It's a gas. We're forming sulfur trioxide, molecular compound. Assume it's a gas as well. Balancing that, we have, let's try 2 here and 2 here. See how that works. It gives us 2 sulfurs, 6 oxygens on both sides. Okay, so we have a 2:1 to 2 ratio. Now, this is a type B problem because we don't know which mass is excess and which one is limiting. So what we have to determine is, okay, the mole ratio between sulfur dioxide and oxygen is 2:1. We have to figure out if what's available exceeds a 2:1 ratio or is less than a 2:1 ratio. So the first thing I would do is calculate some molar masses of my reactants. I'll pause there at that point and do those. Okay, just encourage you to use subscripts here for your molar masses. Try to line it up underneath, sort of in columns. So those are the molar masses of the 2 compounds. Now we need to convert from the given mass, which I'll write down, and I'm going to convert to moles, but first I'm going to convert into grams, okay? And there are 1,000 grams for every 1 kilogram. So those numbers are going to get bigger by a factor of 10 to the 3. So I'm just going to go 4.55. And instead of writing 4,550, I'm just going to write 4.55 times 10 to the 3. And I'd like you to be comfortable with seeing scientific notation a little bit more. So nothing has changed about the number. It's still 3 significant digits. It's just gotten bigger because we've changed the unit from kilograms to grams. Kilograms cancels out here. You can see how that works with the rate conversion. Let's go and do the same thing for oxygen. Okay, so oxygen is a gas, but gases have a mass, 2.88 kilograms. Multiplying that by 1,000 grams in a kilogram, and again that's going to go to 2.88 by 10 to the 3 grams. Okay, so we've got mass of O2 and mass of SO2. Okay, I'll pause at this point. Next step is to calculate moles. Okay, so I've calculated the mass. I'm now converting mass into moles using the formula. I'm getting 71.0. Carry one more digit, which I've rounded up to 3 moles. And then I divide the 2.88 thousands of grams by 32 grams per mole. I get 90 exactly, 0.0. 3 significant digits in both. So now I'm going to compare what I have to what I need. So remind yourself that this is an amount that's available, so this is what you have. Okay, so it's a have versus need. The balanced reaction equation has 2 parts to 1 part. Okay, so that means that if we go from oxygen to sulfur dioxide, we need twice as much. So amount of, or what we could do is just, if we use symbols here, we can say moles of SO2 needed equals twice moles of O2, which would be 180 moles. Okay, and then at that point you can say moles of SO2 available is less than 180. So therefore, SO2 is the limiting reagent. Another way you could look at that is you could take number moles of sulfur dioxide and divide it by 2, and you can see that you have more than enough oxygen. You have clearly quite a bit more than half of 71. Okay, so I'm not going to show that, but that would be another way of presenting that. So the moles of sulfur dioxide is what we want to work with. So the 71.03 now becomes our stoichiometry value. So we're at that point now where we've converted mass to moles, and now we need to apply a mole ratio. And the mole ratio that we're going to apply is going to connect us over to the product side, and we have the 71.03 moles of SO2. And let's look at our balanced reaction equation. The balanced reaction equation is a mole ratio of 2 to 2 for sulfur dioxide to sulfur trioxide. So the mole ratio is number of moles of SO3 equals number of moles of SO2. So that means that if all of the 71.03 moles of our limiting reagent are consumed, we would predict that 71.03 moles of SO3 is formed. And at that point, we can get up to a mass of SO3 by simply calculating the molar mass. Off to the side here, we can get the molar mass of sulfur trioxide, which would be 80.06 grams per mole. So that's how heavy 1 mole of sulfur trioxide is, which means that if we have 71 moles, we would have 71.03 times the 80.06, and our final answer in grams is going to be 5,686.6. So I'm going to round that to 3 significant digits, which means I can keep it in thousands, but I have to round to 5,690. Okay, so the actual answer would round up in the tens place. Okay, that holds to significant digits rules. The 0 that's trailing in that number is not significant. Okay, alternatively, I could write that as 5.69 multiplied by thousands of grams. Okay, sorry, a little bit crowded there, but that's the final process. So that's actually a stoichiometry question from start to finish, involving also determination of limiting reagent. So that's about as difficult as it gets for this course. So if you're at that point now where you're kind of wondering how much further, this is it. Limiting reagent is the last thing we really need to know before we start to look at maybe different types of reaction conditions, like gases and solutions. Okay. So you can sort of breathe a bit of a sigh of relief here at this point if you've kind of been really applying yourself and doing your homework. This is kind of the culmination of this quantitative calculations for the most part with the mole. So we'll look at yield of a chemical reaction later, but again, that's going to come back to determining limiting an excess reagent. And percentage yield is a really simple concept that we'll close off chapter 5 with. So this, again, another section we'll take our time with. We've got some independent work that you should be trying throughout the next couple days. That's shown there in part A. And then some more group work that I think you're being successful at in class, discussing questions and then working on a question with your partner or partners with the iPads. So looking forward to viewing those videos. And again, I'm adding another optional bonus lab exercise, or if you want to continue doing things to boost your thinking inquiry mark, then that's on page 232 as well. So we'll see you in class tomorrow.